And so we had sort of set up the idea of, so this is sort of like where we're at. Where we're at. So we had defined the idea of a parameterized surface. So I had a map phi of variables u and v. That map phi, it eats a domain D, which is in R2, and it produces a surface S, which is in R3. As an example here, we looked at phi of u and v is equal to u, v, u squared plus v squared, so that's a paraboloid. We had defined the tangent vectors. Tu, which was equal to the x with derivative with respect to u, y with respect to u, z with respect to u, and the tangent vector tv, which was x with respect to v, y with respect to v, z with respect to v. And then we'd also noted that tu cross tv is perpendicular to S. So the other word that's used for perpendicular here is normal. It's a normal vector. So the picture that we can draw to sort of keep track of what's happening here is we have the UV plane. We have some sort of domain in the UV plane, D. The map phi takes that and turns it into a surface, so kind of bends it and wobbles it in R3. That's the surface S. This is the map phi. The surface is produced by applying the map to the domain D. That's what that notation means. And if we drew curves inside this domain, so I drew a curve where I hold the v values constant and change the u values, I don't necessarily get straight lines over here because it's not a function, but I do get a curve. There's some sort of twisty curve that might live inside the plane. So the image of that red line is this red line. And if I held all of the u values constant and drew another line, that's going to give me a different curve. And the point is, where those curves cross each other is a point here. And if I want to keep track of how that surface bends, I can imagine taking a little tiny bit of change in the u direction over here, and what the tu vector does is it says what happens on the surface. So the tangent vector to that red curve is the vector tu. And if I made a little tiny move in the v direction over here, and I kept track of the tangent vector to the blue line over here, I would get tv. And tu cross tv is the normal vector to the surface here. These are both tangent, so they sit inside the tangent plane. So a normal vector to the tangent plane will be the cross product of those. So this vector is tu cross tv. So that's the sort of picture of the geometry of what we've done so far. This is what we talked about last time. And the next thing I'm going to observe here is I'm going to be interested in trying to figure out surface area of this thing, or the flux of a vector field through it. And so to do that, I'm going to want to be able to break the surface up into little tiny chunks of area. In the same way that when we worked with curves, we broke up curves into little tiny chunks of arc length. I want to break the surface into little tiny chunks of area. So one really natural way to do that would be to say, if I had a little rectangle over here, defined by the vectors, these two vectors, sort of du and dv over here, and I pushed them through the map, well, that parallelogram formed by those two vectors turns into a parallelogram formed by these two in the tangent plane. These two vectors got sent to these two. The parallelogram that they form got sent to a parallelogram here. And I bet I know the area of that parallelogram. How do you calculate the area of a parallelogram formed by two vectors? Magnitude of cross product. So the idea is that I know the area of that parallelogram is the cross product of, is the magnitude of the cross product. So we're going to define something called unit surface area. The symbol for it is going to be ds, capital S here, because I'm breaking up the little serifs here, just mean that this is a capital S. D capital S is going to be the area of the input thing here. If this is du by dv, and this kind of looks like the change of variables theorem, doesn't it? I have a little bit of du dv here over here, and I'm sending it over to a parallelogram over here. ds is equal to the magnitude of tu cross tv times du dv. That should basically make your brain light up because it's the change of variables theorem. Change of variables theorem says, hey, how much do the vectors distort as you move around? So this is called our unit surface area. This should remind you of d little s. D little s was the magnitude of the derivative of r prime of t dt. So unit arc length was the magnitude of a derivative times length. Unit surface area is the magnitude of some derivatives times area. This is where this idea originally comes from. So that bit right there is unit surface area. And this is just to compare with this. So the observation about this picture, so I'm going to redraw this to be slightly more accurate. What we're saying with the ds unit is the following, and I can't prove this in this class. You'd have to take Math 304 if you want to see an actual proof of this. Is that if I have some sort of part of a surface like this, and sitting inside that surface is a little tiny chunk, and I want to know the area of that surface, of that little piece of the surface, what I could do is I could replace that little chunk of a surface with a tangent plane that sits over the top of it. And the claim here is the area of that parallelogram is about equal to the area of the curved surface that it sits over the top of. So if I took a surface and I broke it up into a bunch of these sort of like fish scales, is one way of thinking about it, and I want to know the area of everything, but it's curved and that's hard to do. So what I do instead is I say, well, I'm just going to basically approximate the surface with these fish scales. And parallelograms are pretty easy to calculate the area of because I can do it this way. Each parallelogram will have an area corresponding to this. And the claim is that if you do this with small enough rectangles, that the area of the planes that you replace the surface with, the scales, that the area that you get is actually the surface area. So I can calculate the surface area of the curved part by adding up these parallelograms that approximate it. And that gets us our definition of surface area. So the surface area of S is the double integral over d of ds. And that should remind you of our formula for length, which was the single integral over d little s. The length of a curve was the integral of ds, where s was the little s. The surface area of a surface is the double integral of d capital S. So as an example, I could say compute the surface area of phi of uv is equal to uv u squared plus v squared. where u squared plus v squared is less than or equal to 1 in the first quadrant. So what we're looking at here is our domain D looks like this, quarter of the unit circle. And the surface that we're producing is 1/4 of a paraboloid. So you can think of the paraboloid looks like this. And we're calculating just this part of it. So surface area of a quarter of paraboloid, sitting over that region right there. And so what our definition is going to say, our definition of surface area is going to say, I can do that by looking at the idea of chopping it up to a bunch of little parallelograms and adding up their areas. The double integral over the domain D that produced it of ds. That is the surface area. Surface area is equal to the double integral of the surface component. And that is going to be the double integral over d of the length of tu cross tv. Oh, man. I guess I should do some math. Okay, so I'm going to need Tu, which is equal to 1, 0, 2U, and I need TV, which is 0, 1, 2V. That's the U and V derivatives of phi. I'm going to need Tu cross TV. So that's I, J, K, 1, 0, 2U, 0, 1, 2V. This turns out to be equal to minus 2U minus 2V, 1. And the magnitude of that is equal to the square root of 4U squared plus 4V squared plus 1. Or if we like, the square root of 4 times U squared plus V squared plus 1. That's nicer. So just calculations so far. And what the definition says, that if I want to know the surface area of that paraboloid, it's the double integral over my region D of this quantity, 4 times U squared plus V squared plus 1 times du dv. Whatever that integral happens to be, that's the surface area. And the way I want you to think about it is, this is the area of a parallelogram. That is what the ds unit here, that is what this represents. Area of parallelograms. The length of a cross product corresponds to the area of a parallelogram. Now this question would be a good exam question because you can solve this because I've set it up so a convenient U substitution falls out of it. Since I set it up on a quarter circle, even though there's this horrendous thing inside of a square root, if you made the move U is equal to R cosine theta and V is equal to R sine theta, you could replace this with, I'm not going to do the integral, but the integral from 0 to pi over 2 of the integral from 0 to 1 of the square root of 4R squared plus 1 R dr d theta, and you could just proceed with U substitution. Generally on exams, what we have you guys do is just set these things up as opposed to actually calculate them, because they're annoying to calculate if you don't see this step, for example. Okay, so the quantity that comes out of that, whatever it is the surface area of that. Make sense? Again, I know this is fast, but what I want you to think is, all we're doing here is we're saying, if I cut this shape up into little parallelograms, notice nothing here looks like a parallelogram because it's a curved surface and the sides of these regions are also curved, but I'm just replacing the curved parts with parallelograms. And that is what the TU and the TV get me, is the fact that I can move from this curved picture to a bunch of parallelograms. All right. So once we have surface area under our belt, we are in position to set up all the rest of multivariate calculus. So the first thing we're going to do is, now we've already studied derivatives and surface area. When we did arc length, d little s, the very next thing we did was we defined path integrals and line integrals. That's what we're going to do. Surface integrals. So on curves, integrals on curves, we had the following two cases. We had a scalar function f, which we could think of as being a density. And we set up the path integral of f. Oh, if I integrated over a curve C of the scalar function f times d little s, I'm thinking about this as density times length, so that mass comes out. The way that we calculated this was the integral of f of r of t times the length of r prime of t dt. That's how we defined path integrals of scalar functions. Everything is cool here because that's spitting out a number and that's spitting out a number, so I'm just multiplying two numbers together, so everything is well defined here, right? Scalar function times scalar function. We also had vector fields. So we have a vector function f. We called these line integrals. That was the integral over the curve C of f dot dr, or ds if you like. These are sort of interchangeable. I'll use ds here to really emphasize what's going on. Vector ds. Now we need to be a dot here because that's a vector. This has to be a vector. Remember, we calculated these as work integrals, was how we were thinking about these things. And these were equal to the integral from a to b of the vector field f dotted with r prime of t dt. I can't integrate a vector times a scalar. I have to integrate a vector dot a vector to get a scalar quantity out, right? So this was how we calculated work done. Those were called line integrals. This is path integral, and this is called a line integral. So, if we're on a surface instead, this is called surface integrals, I can set up exactly the same notion. If I'm working on a surface and I want to know its mass, I give you a density function, f, and I want to know the mass of the surface. What am I going to have to multiply by in order to do that? If it's a surface, so it's actually two-dimensional, density is going to be given in what units? Mass per what? Not volume. It's got to be area because it's 2D. It's bent, but it's still just a 2D thin sheet, right? So it's area density with respect to area. So if I want to add up the mass of a thin sheet like this, like the lamina problems, in the lamina problems, I had a dA integral, right? I was multiplying by area. I still want to multiply by area here. So I'm going to define this to be the double integral over the surface of a scalar function f times a quantity that we just defined, d capital S. Density times area. But now the area is not flat, so I don't use dA, right? The area is now the bent area of the surface, so I use ds instead. Cut the surface up into parallelograms, multiply the area of that parallelogram by density, and you get mass. Density times area is equal to mass. And the calculation formula for this is the double integral over d of f, this is going to look nasty, but it's not so bad, f of uv, y of uv, z of uv. I should give myself more room. In shorthand, I'll just write the double integral over d of f times the length of tu cross tv du dv. So I replace x, y, and z with what they're equal to in terms of u and v. and then I multiply by the unit area component, and what comes out will be mass. So imagine that we're looking back at this problem again. And I say, oh, I forgot to tell you, I was actually interested in the mass of this surface, not its surface area. And the density function f is given by f is equal to xy. What's the mass of that surface? So you would say, oh, that means I'm looking at the double integral over the surface of xy d capital S, density times area. And if I wanted to calculate it, I would have to write down, so this is sort of a mass calculation. If I wanted to calculate that mass, what I would do is I would replace x and y with what x and y are equal to. Remember, this is x, y, and z. And I would write down the double integral over my original region D of u v times the ds unit, but I've already worked out what ds was. I put it somewhere. Did I erase it? The square root of 4u squared plus 4v squared plus 1 du dv. This bit right here is area. That guy right there was density. So what I'm doing is I'm adding up a bunch of little masses. That's the interpretation of a scalar integral over a surface. It's the easiest interpretation. Density times area. Yep.
Why did you change the limits of integration from S to D?
So when I'm saying S here, I'm saying if I don't know how the surface is built, I could say, hey, look, that is the surface S. It's a quarter of a paraboloid sitting in space, right? When I go from S, this is referring to just the surface. When I come down to D, I'm referring to, okay, now I've got a specific map phi that makes the surface. So this is like when you go from, in this setup, when you go from the curve C to the variables that actually get it for you, that's the same move here, right? We're going from the surface S to the actual variables that build the surface instead. All right. So we have one more to go here. One more to go, which is, if you think about this as a chart with 4 boxes, really probably these were supposed to be level with each other. We have integrals on curves. We had an integral of scalar functions, integral of vector functions. When I went from path integral of a scalar function to surface integral of a scalar function, I replaced the length of the derivative with the lengths of the derivatives. When I went from scalar function on a curve to vector function on a curve, I took magnitude of the derivative and I just took the magnitudes off. I bet, by your deep appreciation for the patterns of math textbooks and math professors, that even if I don't tell you why, you could tell me what's supposed to go in that box down there. So I'm going to write it without interpreting anything first. The double integral of f, okay, well, if it's a vector field, I got to dot it with something. It's over a surface and not a curve. So maybe there's a version of ds that's a vector version of the surface area. After all, this was ds and this was d vector s, so by the logic of textbooks, if there's d capital S, there should be d capital S with a vector hat, obviously. And I bet if you look at this move right here where we had, the way I got from d little s to d little s with a vector hat was I just took the magnitudes away. I bet you could tell me exactly what is supposed to go right there. Give it a shot. This is just TU cross TV. DUDV. So this guy right here is called vector ds. So I'm going to give it physical meaning in a second here. I know it's like 5. We've just guessed a theorem into existence. Like, hey, look, it fits the pattern, so therefore it must be a thing. So let's take a look at what that actually means. What this vector ds component actually is. What we're measuring when we do f dot ds. Okay, so what is f dot ds? So we've got a little bit of surface. We have the plane that approximates it. this vector is tu, this vector is tv. If I cross tu and tv, I get a normal vector. Now imagine, so that's our sort of geometric setup for what's going to happen here. Now imagine that I also attach to this picture a force vector F, or a field vector F. And probably the easiest analogy to work with here is, imagine that that vector represents the velocity of a moving fluid. If that was the velocity of a moving fluid, some of that fluid would be passing through the parallelogram. And some of it would be passing orthogonal to the parallelogram, right? If it's moving at an angle, some of the velocity of the fluid is bringing fluid through that little parallelogram, and some of it's just going along it. So what does F dot Tu cross dV give you? What are we doing when we dot F with Tu cross dV? F dotted Tu cross dV tells us, actually,
We're just taking the part that's actually going through.
we're calculating the amount of the velocity that actually is perpendicular to the parallelogram. Essentially, if I calculate this projection right here, and then I multiply by the area of this parallelogram, what I get is the amount of fluid that's passing through that parallelogram in a perpendicular direction. You can put units on these things and see it. If this is a linear velocity measured in meters per second, and I multiply that by an area, which is in meters squared, I get cubic meters per second. So the units on that dot product are cubic meters per second. If this is in meters per second, and these are measured in meters, F dot ds is picking up the volume of the rate of volume passing through that little chunk of surface area, which is also called flux. So this is called a flux integral. So flux is a quantity that shows up in all kinds of areas in physics, engineering, and applied mathematics. It's the idea of measuring how much of something is passing through a surface. So the actual calculation here is something like, if I took F and then I dotted it with the vector Tu cross TV, and then I divided by the length of Tu cross TV, now I'm projecting F into the normal direction, and then I multiply by the area of the parallelogram. So this calculates how much of F points normal to the surface, because you're projecting F into the normal direction. Then you multiply by the area of the parallelogram, and what you get is velocity times area, which is volume per time instead. And then we just hide the fact that this happened. And write that instead. Okay, so now we got a complete set of integrals. I want to think about these integrals. The integral of a vector field over a surface is defined in such a way that we naturally think of it as flux. So how do these questions get asked? Oh, here's this is one I accidentally wrote a good exam question. Compute the flux of the vector field F is equal to 0, 0, 1. So that is a vector field with constant velocity 1 in the z direction, if you're thinking about this in fluid terms, through the surface phi of u and v is equal to uv u squared plus v squared, where u squared plus v squared is less or equal to 1 in the first quadrant. So I'm just going to beat this example to death. So what I'm asking is, if I took my picture of that quarter paraboloid, so the paraboloid kind of looked like this. I've got this quarter of a paraboloid here. And I immerse that paraboloid in a vector field where every vector is the vector pointing in the positive z direction of length 1. And I ask for the flux. What I'm asking you is, what is the rate at which, if this was a fluid problem, what's the rate of the volume flow through that surface with that particular velocity? What's the volume of fluid passing through the surface? And the integral you would set up would be, oh, okay, it's a vector field. I don't even need to know the physical interpretation. I'm being asked to integrate a vector field on a surface. And the integral for vector fields on surfaces is this one. The double integral over S of f dot ds. And then you flip to the back of your exam. Go.
Can't you just already know that it's pi over 4 just because geometry is all the z component?
I mean, yes, I'm going to walk through the example because, like, I'm just going to write the math down, but the result is going to be pi over 4. Yes, yeah. You could this particular one is easy enough. You can just leap to it.
On a test, could you leap to it?
Yes, if I accidentally write a question that you can just leap to it and say that geometry, but you better be able to explain why the geometry makes that happen. Right? But I mean, yeah, if it's constant, it's really the integral on the surface is the same as the integral through the domain that created it, right? Because distorting it doesn't change the flux through it. That's well observed. You're undercutting my beautiful problem that I accidentally wrote. So this is equal to the double integral over our domain D of the vector field, which is 0, 0, 1, dotted with our ds component. ds was tu cross tv. So we're going to write minus 2u minus 2v1 du dv. And yes, you get a really silly answer out the other side of this, right? Which is, this is the double integral over d of 1 du dv, because 0 times 2u is 0, and 0 times 2v is 0, 1 times 1 is 1. Yeah, I know. And then you look at that. I didn't rig it this way, but I guess the reason I did this example again is because there's lots of different kinds of integrals we've talked about in here. If I take the integral of 1 du dv of a region D, what am I actually asking you to find? It's the area of D, right? This is just a regular old flat double integral. This is the area of D, and D was a quarter circle of radius 1, which has area pi over 4. So if I can set up problems where you can integrate without integrating, those are the best ones. Right, so the interpretation here is, again, the flux through the surface or the rate of flow of volume through the surface is pi over 4 cubic meters per second, if you like units being attached to things. All right. So in our whirlwind here, surface area, surface integrals, we are now ready to at least see, we can at least look at what the point of chapter 16.8 and 16.9 are. So I don't have time to do them in detail, but I could at least tell you what the two most important, I mean, Green's theorem is the core of all of this. But I don't really have time to give the next two theorems the treatment they deserve, but I can at least state them for you. Yep.
At what point do you switch from going over the domain of like S?
So as soon as so see right here, I did not use phi yet, right? Phi was the map that makes the surface. So this came up, and this is a good question. When I have an S down here, I'm just referring to the paraboloid. I'm not telling you how to build it. I'm just saying, hey, there's a paraboloid and there's a vector field interacting with it. The way I choose to build the paraboloid does not change the flux. Once I pick a construction, I pick the map that makes the paraboloid, which is that phi of u and v is equal to uv u squared plus v squared. Now I'm creating that by feeding in this set. So the D is the set that I use to build the paraboloid. Once I pick a parameterization, then I'm working with the domain of the parameterization instead of the surface. So you'll see this in your physics and engineering books as well, where they'll flip back and forth between the surface and the domain that was used to create it under a particular parameterization. All right, so the two big theorems here are called Stokes' theorem and Gauss's theorem, which is often also called the divergence theorem. So Stokes' theorem basically takes Green's theorem and puts it in 3D. That's what Stokes' theorem is. So remember, Green's theorem said, so we'll put Green right here. This is where all this originally came from. Green's theorem says the integral on a curve C of f dot dr is equal to the double integral of the curl of f dotted with k dA. Right, that was what Green's theorem said. Rotations inside the domain corresponded to circulation through the boundary. If I can add up all the curls in the interior, I can tell you there's a relationship between circulation on the boundary and curl in the domain. I guess the version of this we got originally was the double integral on d of dq dy or dx minus dp dy dA, which I think I argued in here picked up the rotation of the vector field at all these points. So rotation on the inside corresponds to circulation on the outside. Stokes' theorem says the following. If I gave you a curve C, and I just let it float in space, it doesn't have to be flat, I'm just drawing it flat for the ease of drawing the picture, and to that I attach some surface S. So this is called a surface with boundary. It has an edge. So the surface has an edge. So you're supposed to imagine this is like a balloon. You could reach inside this thing. Stokes' theorem says, well, what I could do is I could cut the surface up. I mean, what we've been doing over here is I could cut this surface up into these little parallelograms. And those little parallelograms will each have a normal vector attached to them. And I can calculate that normal vector because it's Tu cross Tv. And if I have some vector field, I could calculate the rotation or curl around each of those, right? So there's a curl around that vector. And there's also a tendency to rotate around this vector. And I could rotate around this vector. And if I add up all of those tendencies to rotate on all the little parallelograms I've cut the surface up into, then all of the combined effect of all those rotations is equal to the circulation on the boundary. So if I wrote it down in symbols, it says the integral around C of f dot ds is equal to the double integral on the surface of the curl of f dot d vector s. Circulation in the boundary is equal to the sum of all of the tendency to rotate in the surface. So you can imagine, it's like I took Green's theorem, and I imagine this was a bubble, and I just blew into Green's theorem and puffed up. So what Green's theorem would say is something like, here's our curve, and we have this flat boundary inside of it, and Green's theorem says, oh, if I add up all the little tendencies to rotate on the inside, then what I pick up is the total work done on the outside, right? So if I got underneath this thing with a fan, and I blew the fan into the sheet, and it puffed up into a balloon, Stokes' theorem just says it still works. I can calculate rotations in the surface, and it will still be equal to the rotation in the boundary. Yep.
So this could be any surface.
Oh, yeah.
That has the
Any boundary. So a typical trick with Stokes' theorem in practice is you get some god-awful surface that you want to know the curl through because you're working with some sort of field operation, and you say, man, that surface sucks. But the surface rotation is equal to the boundary circulation, which means I could replace, but that's equal to any other surface I plug in. So the rotation through these surfaces with the same boundary have to be equal to each other. It's called the Stokes trick. That surface sucks, so squish it flat and calculate its curl, and it's the same. It has the same boundary, which must have the same rotation. Right? Stokes' theorem says rotation of the boundary, circulation of the boundary is equal to rotation of the surface. Who cares what surface is plugged in? Squish it flat. Same answer. Yeah, so Stokes is the 3D version of Green's theorem. Yep.
But the rotation around the boundary is the same thing as the work done.
Yes.
If you went through it.
Yeah.
Okay.
Yeah. So that's the way. Yeah, circulation around the boundary is work traveling around the boundary, right? So this is essentially like Stokes' theorem is a thing that says even if your vector field isn't conservative, there's something like a conservation law happening, right? Because the amount of energy that you got going around the curve, whatever the work done that you got going around the curve, is equal to some tendency to like some inertial component in the vector field, and it does not matter how you traversed the vector field, that stayed stable as you did it, right? If you know what the total work done was, these have to balance in some way. Okay, so the divergence theorem is a theorem about flux. So I'm going to write down the divergence theorem, and we'll see if I can justify that one. Don't need to worry about having to use these things, by the way. I just want to have at least shown you like Stokes' theorem, because if you have to do this kind of math, you will see this. And if you have to take physics 3, which I think is the electrostatics class, then you will have seen the divergence theorem in some form. So the divergence theorem says the following. I'm going to write it down, and we'll try to interpret it. The double integral over, okay, I guess we should start there. This is a theorem about what are called closed surfaces, which means no boundary. So, for example, a sphere is a closed surface. There's no edge to a sphere. Or a donut is a closed surface, or a double donut. Closed surface, right? You can punch as many holes in a donut as you want. It still stays closed. There's no edge. So what Gauss's theorem says is the following. A simpler shape here might be something like if you took a paraboloid and you put a cap on it. So you actually closed up the top, like putting a lid on a coffee can. That would be a closed surface. A cylinder with both ends attached to it. Gauss's theorem says the following. The double integral on the closed surface, a lot of times this is written with this hilarious symbol, which means it's a closed surface, of f dot ds. So this is a flux integral, is equal to the triple integral in the interior. So I think E is the inside of your closed shape. So E is on the inside, and S lives on the outside. E is the interior of the shape, like the ball part, and the sphere, which is its boundary, is the S. Of the divergence of F dV. So that's the divergence theorem, or Gauss's theorem. So what's the interpretation here? What you're claiming is the total flux through a surface is equal to the divergence of all the bits on the inside. So the way to think about that would be, what does divergence measure? I've got to say, you're going to break your volume up into these little cubes. Divergence measures the difference between the input vectors and the output vectors, right? So if you had a cube, the change between these two vectors, that's what we measured as dp dx. So notice what would happen if you glued another cube onto that cube. I'm going to separate them, but imagine that these were cubes that are sitting right next to each other. So the output of this cube is the input of that one. Then the input vector here would be this one. That vector, even though it's the output for this cube, it's the input for the next one. And then this has, like this vector as its maybe something like extra long as its output. What the divergence theorem is saying is, if I want to know, or that whatever happened to the inside must have canceled, the only thing that contributed to the net flow through the surface was the difference between the input vector over here and the output vector over there. The divergence canceled everything on the inside. The output from that cube was the input to that one, which means they have opposite signs. The divergence here was the difference between these two vectors. The divergence here is the difference between these two. So you can imagine if this is vector 1 and this is vector 2, this is vector 2 and this is vector 3. The divergence of this bit was 2 minus 1. The divergence of this bit is 3 minus 2. If you add those, you get 3 minus 1. The outside is what mattered. Nothing in the middle. So that's all that the divergence theorem is saying. Whatever the vector field is doing, expanding or contracting or flowing in the inside, its net effect of adding up all the divergence on these little cubes must be equal to the flux through the surface as a whole. You may have seen this theorem, like this theorem gets used in electrostatics. I think prove that the flux of an electric field through a closed sphere is 0. Like you put a charged particle on the inside, you get 0 flux through. what is the theorem?
On the outside.
What's that? On the outside. On the outside. Yeah. Yeah. So that's a consequence of the divergence theorem. You can tell how long it's been since I've taken physics. Right. So that's basically an introduction to these big theorems. You don't actually need to, I guess I could make you responsible for them, but I haven't really had a chance to talk about them. I'm not going to assign homework on 16.8 or 16.9. I just wanted to be able to introduce you to these ideas. If you go on in this type of mathematics, you will have to use these theorems because flux of fluids or flux of vector fields turns out to be really important. And rotation or curl of vector fields is also really important. So lots of physical applications of these guys. My plan for Thursday and Friday is Thursday I'm going to do, we haven't done a problem session in a while, so Thursdays will be about the stuff on 16 that you need to know. So we'll have one lab day on Thursday, which will be like, let's just do a bunch of these integrals. I'll give you the formula sheet that you'll have on the final so you can see exactly how it works. And then on Friday, for those of you that are interested, I'll run a mock. I'll just bring in a final. I got 2 of them. So I'll bring in an old final. You take a look at it, see how you do. If there's anything else I can do for you, I'd be happy to. I'll start putting up review materials as soon as I can. I would love to spend more time talking about this. For those of you that are interested, if you want to look at further resources, I have some things I can offer you. There's really beautiful explanations of these things on YouTube. For example, I think 3 Blue 1 Brown has a nice video set on multivariable calculus. It kind of goes into what these things are measuring. Okay. So, the last thing I'll say before I go today, this doesn't need to be on video.